And we're more than pleased to be welcoming our presenter, Ron Cohen, with Classiq Technologies. So Wolfram is very excited to be working with Classiq in the realm of quantum computing. So as people try to come up with practical devices that can implement many of these quantum circuits, the science of quantum information proceeds at great speed, and innovations are being made all the time, which are very exciting. So because the computational world is so large, there are folks like Classiq that are true experts in figuring out how to bring what is being new and developed in the realm of quantum computing as a service to people that are out there that want to both know more with educational events like this, as well as look at these things as they will impact industry as the quantum computation industry develops over the years. So we're very happy that our presenter, Ron, can join us, and very happy that all of you can join us in the audience.
Thank you so much, John. Actually, I'm much more excited than I thought. Also because I'm a big admirer of Wolfram Mathematica. Back to my bachelor degree, like when smartphones started, it was and still until today one of the best main tools to make research and mathematical analysis. So I studied electrical engineering. I did not know anything about quantum computing at that time. Later on, I discovered this amazing world and did my research at this field of simulating quantum error correction, actually, a world which is a bit different from quantum algorithms, and started to work at Classiq 2 years ago. And I'm excited to work there. I'm a quantum application engineer over there. And to deliver this workshop, this exciting workshop to you. Actually, the application that you will see today is based on works that we started with Wolfram about a year ago for use cases that show how the integration is enhancing application, actually taking the benefits both from Classiq software for quantum algorithms and from Wolfram Mathematica environment, which is amazing tool for so many things and adapt so well, as you will see today, to develop real-life applications. So as been said, please feel free to ask questions. There is also John and Tamuz, which is also in my team. He's a quantum application engineer in Classiq. He will also answer questions, any support, of course, that you need, any general questions that you have there. Please feel free to ask. As John said, I also recommend, if you want to run the code live, it's better to register to the platform even before. While you are, it's important also to listen to the presentation to understand what is going on. But of course, it's really okay if you don't run any code and you just listen. It's really, really okay. You will get the notebook and you will be able to use, if you have a Mathematica environment and registering to be a Classiq user, you can run it by your own as a homework. At free time, you have the solutions. Everything is very well explained, so you can just enjoy the next 2 hours. Listen, follow up, and understand. And that's it. So let's begin. So we will talk today the next, let's say, next 40 minutes. We want to give some introduction to understand what are we talking about, what is quantum processing, quantum computing anyway, what challenges do we have, what is Classiq and this integration with Wolfram is, and which challenge it's coming to solve. We will explain what is the Classiq language, which is a it's a high-level abstraction language for developing quantum algorithms, and then we will explain what we actually the workshop is about. The specific use case that we chose is simulating differential equations with quantum algorithms. So we will explain the mathematics We will learn how it's going on, the formulas, everything, and then we will do the actual workshop. This is just one use case we are doing. There are more, and I will refer you to see where in the community you can see how to explore more fields that you are interested about, whether it's finance or cybersecurity, chemistry, whatever. Everything is very interesting to develop this environment of integration between Classiq and Wolfram. Okay, so quantum computing, what is it? Anyway, so for so many tens of years, there is the theoretical idea of a quantum computer. I don't know if you saw this kind of picture before, but when we are talking about a quantum computer, it is a computer that is able to store actually quantum information. So we will see what is different between a bit and quantum bit, different between quantum and classical computer. And it allows us to make better performance in different kind of algorithms in different domains: chemistry, finance, pharma, differential equations, as you see today. And I would like to give just maybe to understand what is a quantum computer. So the best thing to do is to understand what is a quantum bit, or as we say, a qubit. So I guess most of you is from some scientific background, so you know that a bit is 0 or 1. This is how we encode information, whether it's numbers or pictures or whatever. So each bit can store at the time just one value of 0 or 1, and we can build a full language with zeros and ones. Now, the idea of a quantum bit is that the fact that we can store 0 and 1 at the same time, at the same just one qubit. So I try to ask ChatGPT to create this picture that will explain that you can imagine two pools and you have waves in these pools. So it's very much like there are waves in both of the pools. So I see the height of the waves in each pools, and it's give me much more information. So there is the height, and there is the phase of the waves, and there is the 0 and 1, like a digital and amplitude and phase. More places where I can encode actually information. You might wonder what is it physically in the real world. So maybe the best is to think about when you take a laser, some beam of light, and you shine it over a splitter, so you get 50-50, two lasers. So when you, instead of a laser, sending just one particle of light, just one photon, so the photon is at the right and the left at the same time. So this is kind of a way to create a quantum bit, actually. But we are not talking about physics today. We are taking this mathematics, we are assuming this is a fact, and we see how we develop algorithms with it. So if we say that a bit is 0 or 1, so a quantum bit can be a alpha 0 and beta 1 at the same time. We say that alpha and beta are the amplitude or the probability of 0. We say probability because this wave, even though it exists in both time, what we see is that when we measure if this is a 0 or 1, it never both. It's always just one of them. So if you measure if the photon go to the right or the left, it will be always just one of them. And the probability to see if it is a 0 or a 1 depends on this amplitude, on this alpha and beta. So this is the probabilistic nature, but before I measure, it's not probabilistic. It's the same. It's in both places at the same time. Now, this is what happens when we have just one qubit, but we want to understand the power of quantum computer, but by adding more bits. So what happens when I add one more qubits? So there are 4 options: the 0, 0, 0, 1, 1, 0, and 1, 1. And each one of them has another amplitude. So I get four pieces of information. And when I have 10 qubits, so I get 2 to the power of 10 combinations. So this is roughly thousands pieces of information, thousands of amplitude by only 10 qubits. And if I take just 100 qubits, which is not a lot, it's less than a kilobit, so I see 10 to the power of 30, like 1 and 30 zeros of amplitudes. And so it already gives us the power of a quantum computer. But besides the power, there is also the challenges, of course. Today, the computers are very much like Tamagotchi, small computers. There are a lot of challenges from the physics to the engineering and the algorithms, so many challenges on the way. Today we are talking about computers with, let's say, just 1,000 qubits, but these qubits has noise, they are not accurate, and we need to build error correction schemes. So each qubit I have to be encoded in many qubits just to correct the errors, and the scalability is not trivial engineering challenges. So there are very interesting challenges in the engineering and physics world. But today we are coming to talk about the quantum software challenge, which is what we are coming to solve with the Classiq platform. The idea is exactly like classical computers. If we go tens of years ago, let's go 60s, 70s, when engineers developed the classical computer, so it was very challenging to code into it. So they started with the punch holes on cards, and then the assembler, which is a gate level machine. And of course, it's not practical to develop applications or ChatGPT or something very complicated with a low-level language. And this is why during the years they developed the C and C++ and Python and MATLAB and Wolfram Mathematica, the high-level languages that are useful to practically develop easily the application. Not that it is impossible to do it this way, but it's grossly impractical. So now we want to see how it's done with Classiq once we understand what is the challenge that we are trying to face with. And this is exactly the kind of challenge we are dealing with now with quantum computers, that we have a gate level software when we want to develop complicated applications. Besides this problem, there is another problem that when we see big companies that there are billions of dollars around the world are invested in quantum computers, also at the application side. So when someone wants to develop any algorithm, so he needs to choose on which hardware to run, so it affects the low-level code that he's writing. And this is also something that we are coming to solve. You are writing just a high-level language, and the Classiq compiler is adapting it according to the hardware that you just choose with preferences. So this is another challenge that we are coming to solve. So let's understand what the platform is actually. We're coming to be a gate to all of the different hardware providers. We already see that Amazon and Microsoft, IBM, they are providing the quantum computer access over the cloud. We are integrated to it, giving the access at the high-level language and compilation, which you will see in a moment. So the platform is made of, I call it like 5 main components. The library, we have a rich library, as I said, so many different kinds of applications you are interested in. And you can explore and find something that you like, download it, read it, the deductive material too. Maybe I will show some example. Our user guide is open to everyone. You can explore over here your favorite application, whatever you like. You can also see it as a Git repository, so you can just type classic Git in Google and find these examples over here. We welcome you also to contribute to this library. This is open for everyone for contribution. And all of the examples are also available for those of you who already registered. So these examples are available in one click over in our platform once you are logged in. So this is the library, and there is the model, the high-level language, and I will explain about it in deeply. Idea of types, not just a qubit, but more than it, we will see in a moment. Compilation, so we choose the hardware and we can compile to the hardware that we choose or any custom hardware and design. Visualization, interactive one, inspired from CAD softwares, and execution for parsing the results and integrated with different kind of also quantum hardware backends, but also a simulator like a NVIDIA GPU simulator to mimic a small computer with up to 30 qubits to give you quick and accurate results for your POC, proof of concept. So the platform can be accessed in two different ways. One is from the classic platforms that I showed you before. The other one is a Python package. This is how we do it also in Wolfram Mathematica. We can import the package, we can write the algorithm and run it from Python. From both, we can do the same things. Classiq is we exist for a few years, and we are working with some big companies around the world. One of our clients is BMW, for example, who are making optimization of cooling system with Classiq, the integration with Wolfram, of course, a partnership with NVIDIA, Citibank, HPE, Microsoft, and also a community around the world of thousands of users. I will show you also the Wolfram community group in this community, delivering hackathon very soon in MIT hackathon, IQ Hack. I welcome you to register. And it's end by the registration is end by the end of January, actually. So highly recommended, a nice challenge. So this is Classiq, and now, as I said at the beginning, it is very natural and beautiful to integrate with Wolfram Mathematica. As you will see today, we can do very beautiful things. You will get a PDF of this presentation, and you can click and watch the YouTube when we explain about the integration. Over there, we demonstrated two examples. So we explain about presentations, both about chemistry and about finance examples. So I welcome you to check it over there. And there is also the Slack community, where we have really, it's very nice, like thousands of users are asking questions, asking each other question. And you can join over there and join the Wolfram Classiq community, which is not very active currently. And this is one of the reasons we are doing the webinars. We are trying to make more interesting project together with you, with the community. So I welcome you to join. It's also available in the link over here. And maybe we'll also, in a moment, send it in the chat so you can see both of it. Okay. John, Anything else you would like? We are going together for a long way, already a year together. Would you like to tell about the integration too?
Yes, actually, I see a Q&A question about, what do we mean when we say integration? So Ron was just talking about the platform that Classiq has. Again, there's a variety of resources that they have. So one would be the browser-based interactive development environment that you'll see a few more times in the practical example later. They also have a library, which you can use both from working with Python, but then also from within a Mathematica notebook, you can also use what they call the QMod language. So this is that high-level language that is for doing programming that leverages the power of quantum circuits without the programmer having to go all the way down to worrying about the physics of what's going on in this quantum circuit, right? So as Ron was saying, the place that the quantum computing industry finds itself in is much the same as what regular computing found itself in before computer engineers had sort of built this very convenient tower of abstractions that lets people who are writing let's say you're using Wolfram Language code, you don't have to worry about what the computer memory is doing way many levels down, right? So, the mission of Wolfram has been to bring this ability for people to express what they want to do to the computer in language that makes sense to the person, and then the details are implemented in such a way so that the computer does what you want to do. So this is, in many ways, the same challenge that quantum computing finds itself in right now, that as people are looking at these applications and folks are wanting to leverage the power of advancements that happen in hardware, languages like QMod are a way that people can use a lot of very, very, in fact, Ron, you might at some point get more questions about, so technically, what are some of the challenges that, that function that synthesizes a circuit out of the high-level description? There's actually a lot of fancy things that go on to make that happen in a useful way. So there are a lot of details about how you take a high-level idea and actually turn it into something that can run on either a simulator or today's hardware, and then the hardware that will be coming out in the future. So in order to circle back to what the original question was, Classiq offers these options in the realm of quantum computing, and as someone that has been doing many of the same things in the classical computing realm for many years, it makes sense to have this partnership where Classiq has developed a lot of great tools that they really specialize in taking a high-level representation of a problem and then turning it into something that can usefully be done on quantum hardware. So when we say integration, this is the sort of thing that we mean, is that by using the Classiq library that you can access through Mathematica, and you'll also see in the practical example, taking the circuits that come back from Classiq and importing them into the Wolfram quantum framework so that you can study them there. Really, there are some functionality that we're quite proud of in terms of being able to visualize and analyze problems in Mathematica, and we're leveraging the expertise of Classiq in how to turn high-level descriptions of problems into useful quantum circuits. So hopefully that clarifies the question on what do we mean when we say integration.
Thank you so much, John. Great. Okay, so let's go a bit deeper and understand technically what is going on. And we will start with the language. You already saw the library and the different examples and different ways to access the library. So the idea when we develop a high-level language, there are few kind of things that we should consider. So first, we would start with types. And anyone that is familiar with classical software knows that you can create variables that can be just a Boolean, a bit, true or false, which is like a qubit, which needs just one bit. And you have double and float or fixed point precision to represent numbers that can be negative or positive. So this is another thing that is special in classic language, the fact that we have quantum types. So if I have a quantum number, which behind the scenes is actually made of few qubits, one of them represents the sign. So there is the superposition. We say that in the quantum world, maybe it's worth saying it now, that in the quantum world, things happens at the same time. So we can think about it like parallel worlds, actually. So when I said that a qubit can be a 0 and 1 at the same time, so we can think about two worlds that exist at the same time. We do it by starting with something and make some operation on it. So we can move the probability to be bigger for the 1 or bigger for the 0, but it's 2 at the same time. So as you can see, a qubit over here, my mouse is too sensitive. As you see a qubit over here, so we see a type of a qubit, allocation of 1 qubit, and then I am applying operations. So X, for example, is a flip operation, which is everything that was a 0 becomes a 1 and the 1 becomes a 0. So in the quantum world, it means that the amplitude of 1 and amplitude of 0 are changing. And there is the Hadamard gate, which is something that starts from a state that is just 0 all the time and split it to be a 0 and 1 at the same time. And if we think about the quantum number now, so it means that if we look at the qubits that represent the sign, so the number can be positive and negative at the same time. And I can have fraction places, so I can be at the same time minus, in one word, this register is containing the number minus 1.25, and in another word, it's containing the number 3. So I create a parallel words of quantum numbers, something that is unique in the language. And then something that is trivial in classical languages, the fact that I can do A equal B plus C, or multiplication, it's obvious, but behind the scenes, there are so many small gate level operations that we should do. And this is the kind of thing that the classic software is giving us. We are jumping from gate level operation, from assembly to a high level, like a C language, let's say, or MATLAB or Python. So behind a multiplication or addition, there are many quantum gates, and it means that this operation are happening in parallel worlds, actually. So if X and Y have different values and different worlds, so in each one of this world where X and Y have the some value, so Z has a value which is a summation or a multiplication or any arithmetic operation of it. So in different worlds, Z, the result, has different values. And this is the parallelism over here in quantum computing that we need in the algorithms that you will see soon, is allowed by a high-level language, which is not possible in alternatives ways, or very convenient, as you see over here. And quantum arrays can be an array of qubits or array of quantum numbers. And if having this, why not having quantum struct for object-oriented? So a quantum struct can be composed of a qubit and the quantum number, and we can access it like an object-oriented language. Everything is, again, in a quantum world. So this is kind of thing that is unique in the language, and it is allowing you, as John said, to easily define your own applications. Maybe before I continue, I would just like to show you a small example, just to make sure you are not confused and to demonstrate what I'm trying to say. I would like to show you an example of something we've done with Intesa Sao Paulo Bank in Italy. We published an article, they published in IEEE, they developed an application for pricing options. This is the code that they wrote, it's pricing options. So you can see the quantum struct over here. So there is an object that is containing two assets, two prices of assets. Each one of them is a quantum number, so I can load distribution of prices and to estimate the expectation value and the risk on these assets. So once we have quantum numbers, we could have easy discussion with the guys that did not have a quantum computing background, and so they got a short training, and we could easily define together kind of arithmetic functions that are coming from their financial world easily into the quantum world without knowing much about quantum at the beginning. And it allowed them, so you see this is the application. It's 60 lines and an article that was published in IEEE at the end of it, thanks to the easy language. Yes, so I would like to show more concepts of the language. So we said 0 and 1. If you remember, we said amplitude and phase. So this is also another kind of areas that we can encode information, not just digitally to say minus 1.75, but also I can put the information inside the amplitude and phase. This is very big algorithms when we think about them at the gate level, but in Classiq we added the option. So this operator is equivalent to this circuit, which is just a short cut-off example of this circuit, and it allows us to encode information at the amplitude. So the amplitude of this qubit, we're getting this quantum number and converting the information from the digital domain to the amplitude domain. We can also encode information in phase. If you know a Suzuki trotter, which is needed over here, so if I have Suzuki trotter is the algorithm behind the scenes to do it, but for the user, he does not care. He just wants to encode this information. And here you see an optimization algorithm of max cut. So there is, you define some function, and V is a quantum variable that represent nodes in a max cut algorithm on a graph. So what you see over here is the phase operator to encode information in phase, something that is also unique to the language. And that's it about the platform. Now it's the part where we start the theoretical background for the workshop. Maybe it's a good time for questions if there anything specific you would like me to answer now.
Yes, there was one question which I think speaks to exactly what we mean by high-level representation versus low-level representation of what you want to do computationally. So we had a question about how do you encode numbers in qubits, and there's various ways that one can do this. And so part of the utility of having high-level languages like QMod is that someone who they might be curious, but they ultimately don't need to know the details of how that's done at circuit level in order to do a computation after the numbers are encoded. So, we will discuss some of the theory of how some of these things are done, especially as they relate to the HHL algorithm. But I think that really puts a nice point on why do you need high-level languages, right? Is that it's interesting to know how you encode these numbers in qubits, but really that's not necessarily the level of programming that you would always want to be doing.
Yeah, exactly. And if you care about the internal details, the idea is that you can also you can explore both. So you can see I prepared a small x equal 2, it could be a superposition 2 or fractional or whatever, and here is the arithmetic, and you can see, okay, here is x, here is y, it's made of 2 qubits, the lines are 2 qubits, and y is also encoding, it's need only 1 qubit, and z is the result over here, and that's it. I can encode the information. It's very much like FPGA, if we go, chip design in the classical world. But if you're curious what is going inside and how can I encode the x equal 2, so you can always zoom in and see, oh, okay, 2 is, there is some way to encode it, and I have to apply inversion gate over here, and this is the actual encoding. And the arithmetic operation, there was multiplication and addition, but maybe I'm curious how addition is done, so maybe I can explore what is going on here. And maybe no, and we will see it later in the example. And then regarding the encoding, it's also important to talk about parsing the results. So when I take the circuit and I measure it and I see what happened, so here you see just a simple example where Z was parsed to be equal number 1. It can have any fraction or whatever, and not at the bit level parsing. So this is regarding the encoding of information. So now we'll start some more mathematics and interesting kind of algorithm for solving differential equations and how it's done. Okay, so let's start with what is a differential equation anyway. So we know that many kind of physical problems in the world are able to be described by equations which are trying to equalize between some derivatives of function, the slope of function in different points, and the value of the functions, or maybe second derivative, etc., etc. So, for example, if we think about how a string behave when we squeeze it, so it's bounce like a sinus over and over. And actually, to show mathematically that this is what will happen, so we know that the force behaves like a second derivative of the change of the spring, and the change of the spring is just change of the spring and not a derivative, so we can describe it and we see how it behaves like periodically. So first, this is differential equations. Today we will see a specific kind of differential equations for the Lanchester model. And now we will discuss about classically how can we solve this kind of problems that are sometimes complicated numerically. So since the slope of the derivative of some function is defined to be like the triangle over here, delta y divided by delta x. So when it's bigger, so the slope becomes bigger. So we can say, okay, let's take just 2 points and we can approximate that the derivative is approximately the difference between f2 to f1 divided by delta x. And as delta x becomes smaller, so it becomes more and more accurate. And the idea of finite difference method is that we can take this collection of all these derivatives all over the curve. So if we know the original, the initial condition at the beginning of the function over here, and we know how to build the derivative in an iterative way, one after another, so we can actually reconstruct all of the function in a numerical way. And this is the idea of finite difference method. Maybe I will show something more graphical over here. Finite difference method, just to give you more feeling of confidence. So maybe let's take a look on this one. So we know that if we start from a specific point, if I know the slope, I can jump to the next one. And if I know the slope over here, I can jump to the next one and build it in an iterative way. So actually, instead of iterative way, I can describe it also as a matrix multiplication. So matrices is a way to compactly define a lot of equations. So we will see the exact example later on, but for now, please assume that what I'm looking for is the vector over here. And if I multiply the matrix by this vector, I get some constant. And this U, they are the things that I don't know, the things that I'm looking for. We are trying to solve and find this U. So what we need to find this U, assuming we can solve the problem by defining it this way, multiplications of unknown variables that represent all these points. So we know that if we apply the inversion of this matrix in both sides, left and right, so we get just this one. And at the right side, we just have to apply the inversion of this matrix over here on this side. But it sounds like, okay, whatever, why do we need a quantum computer to do it? Because in practical world application, just today, this week, I met with a client that say that they are not solving very big kind of big matrices, because when the matrices are too big, the computer just is not able to invert them. They are doing it to optimize the construction. They build materials, they want them to be strong and not too heavy, so they have this kind of a lot of differential equations. They build very big matrices. They are trying to invert them, but it's computationally it's too heavy. And this gives a motivation to use a quantum computer to make a matrix inversion. So this is the motivation, and maybe it's another good point for questions about it before we move to the quantum part. Something specific.
So far, it looks like we don't have any other questions about finite difference method. If people have any others that come up, do feel free to put them in chat, because finite difference method is one of the key concepts that can be done, as Ron said, on a classical computer. However, like many things that can be done on classical computers, there comes a point where it becomes useful to know, well, what's the quantum version of this, because the classical computer might have issues with certain versions of that problem.
Great. Thank you, John. And now, very sensitive mouse, I said. Okay, so now from this point, we have a motivation that we want to invert matrices with quantum algorithms. And in this point, I welcome you to search in Classiq user guide. There are the links over here. There are three main algorithms to invert matrices. They are all available in Classiq user guide or Git library. So HHL, so if you will click over here, so you will get the HHL in the user guide. VQLS, Variational Quantum Linear Solver, which is also available in the user guide, or Quantum Singular Value Transformation, QSVT, for matrix inversion, also available here. You can read for deductive purpose and try to run it by yourself. But today we will focus HHL, which is the name of Hero Hasidim Lloyd. This is names of three researchers who invented this algorithm. And let's see how it works. Now things become very quantum. So we say that our purpose is to apply inversion of a matrix on a given vector. So my unknown variable is x, and I know that x is equal to the inversion of A operated in B. So in quantum computing, since we say that when we have many qubits, so we have list of amplitude that represent them, so we can say that the state of many qubits is a quantum state, and the amplitude of each one of the different states, we can also see it as a vector, actually, a vector where in each row, this is the amplitude of the specific this specific state. Quantum state maybe there is a nice image I had to use. Quantum state vector. Let's try to open some nice example. Okay, so we see over here that the quantum state, each row is the amplitude of a state. So alpha 0, 0, 0 is the amplitude of the state 0, 0, 0. So this is actually a vector. So we can think now as about x, the vector we are looking for, as a vector in the quantum domain. And also b, which is also a vector. And we can find x by applying an operation which is equivalent to a matrix, but in a quantum world, operated on a vector b. So this b is a vector representing some quantum state. If I will be able to apply successfully something that mimic the inversion of a over it, I will get the solution for x. Now, why is it powerful? If you remember, we say that with 10 qubits, I can represent 2 to the power of 10, so thousands of different pieces of information. So it means that I can take a very long vector, length of 1,000 rows of the vector, and represent it in a memory of only 10 qubits. And if I take, of course, 100 qubits, so I represent them, I can represent a vector of 2 to the power of 100, which we say is 1 and 30 zeros after it. So it's huge. So of course you might wonder what's going on, how can we do it, is it already happening? So as we said at the beginning, today the computers are very noisy, we need error correction, we don't have it yet, but once we have such kind of not noisy, good computer, we can represent this kind of vectors with quantum states, with exponential reduction of the amount of memory for a given size of vector. So when people come with, as I said, the topology material optimization, so in their case, they are trying to optimize, they have like a grid of so many different pixels. So when they have, they are trying to find the optimal structure in 100 pixel. So there are 2 to the power of 100 combinations. So it could be better if they could do it with much less memory, like just 100. So this is to give you the motivation. Okay.
We did have a question about is it important how many qubits you use for each of these various things? So you'll see in the practical example notebook there is a section which discusses the number of qubits that you choose to use affects the accuracy of the output of the algorithm. So there are some circumstances in which choosing that parameter of how many qubits to use will affect the final accuracy. And Ron, if you have any other comments about that question, sort of generally, is it important how many qubits you use at various steps?
Yeah, sure. Actually, it's a great question because the slide over here will demonstrate. Maybe the next one will answer more to this question. I would like to explain now mathematically how it's what is going on, and then you will see exactly the precision John just mentioned, where it's coming. So now a bit more of mathematics. We know that we can that every matrix have its eigenstates and eigenvalues, and what it means eigenstates and eigenvalues, that if there is for any eigenstate uj, so there are u0, u1, all of the eigenstates, so for each one of them, when I apply a matrix A on the eigenvector, so I get just a multiplication by a scalar, and then I get the with the same state vector. So this is a mathematical background for to remember that what is eigenstates and eigenvalues, and also a fact that I can decompose any vector to a summation of states multiplied by values, as we will see below. So for example, X can be represented by a summation of all eigenstates of A with the own amplitudes. Now, just another preliminary is if I will operate the exponent multiplied by I of the matrix, so the eigenvalue will come over here in the phase. So it will be just a multiplication by phase instead of by lambda. And if I will play the inverse of A on the eigenstate uj, so I will get the inverse of the eigenvalue applied on the eigenstates. Now, with this preliminary maths, we can say that we know that it's mathematically possible to decompose B, the vectors that we want to apply the inverse of A on, into eigenstates. And it means that if I will apply the inversion of A on B, which is what I want to do, it will give me the solution. We can decompose and look how it looks internally. Each of the betas that are composing B will be divided by lambda, which is the eigenstate of uj, because of this property. Any question about this before we see how it's done in a quantum circuit? And we will go to the actual workshop doing HHL algorithm together.
It looks like we do have a follow-up question about number of qubits. Is it true that the same thing applies if you were using classical methods, that the amount of essentially memory that you allocate can affect the accuracy of the result? And yes, that is true. So just like with many classical algorithms, if you worry about the details of what is the computer doing whenever you're doing anything involving numbers, then it does matter how much memory is allocated. So you can think of how many qubits are allocated for certain parts of this algorithm in much the same way.
Yeah, indeed. We see that it is possible. We need the precision and we add more qubits, but we are still able to reduce exponentially the number of qubits that we need for the actual data.
And it looks like we have another question, which is that they're excited to see how can quantum computing solve some of these practical problems, and how does that compare to classical methods. So I think that is a perfect cue to go into the second part, where we'll look at a notebook that shows some of these things with code.
Yeah. Now what you will see now is just the flow of the notebook. So we see step by step how HHL is happening. So over here you see a short map of HHL algorithm. So we are starting with preparing the state. Just we want to load B first, because this is our input of the problem which we want to apply the inverse matrix of. So with Classiq, it's easy. You can just give the list of numbers that are composing B. It will prepare the vector. Behind the scenes, there are gates for preparing the state, but it's not something that you should care about when you design the application, just when you are interested to dive in and maybe to try to improve things inside. Then coming the quantum phase estimation algorithm, which is very interesting, actually. This is one of the algorithms that are maybe in any interesting algorithms, quantum algorithms that give quantum advantage. In almost all of them, we see the quantum phase estimation. Besides how it works, which we will not talk about, as a black box, when we are applying quantum phase estimation, so when it gets a phase, so it gives you the result. When it gets an operator that is operating a phase, it gives it to you. So maybe it's time to go back to this slide. So if I give A to quantum phase estimation, and I actually applied the exponent of this A, which is applying this phase. So it will give me the lambda in another register as a solution, and it looks like this. So there is a QPE with A, which is applying on UJ. And what happens when I apply the quantum phase estimation on UJ? So this lambda is popping out. So it's almost the solution, right? We just need to divide beta over lambda and we get the solutions that we are looking for, like this. But the lambda is here encoded digitally instead of in the amplitude. So we talked about amplitude and digital encoding before. So the only thing we have to do is to load this lambda to come below this beta, and we actually get the solution for x. We are doing it with the amplitude loading operator. As you saw, it's short and easy inside the language, and we will do it in the workshop together, each part of the components. So it is loading this lambda up to some constant which we can also always divide by, into amplitude of another qubit, just one more qubit to get this amplitude. So as long as we are post-selecting and using only cases where this qubit is equal 1, so we are getting the up to some normalization again. We are getting the solution for x, which is beta over lambda, up to some constant, which we can also fix, and you will see, as long as we know which constant. And this is the idea. Now, it's a good opportunity to say that we are not getting, we have this vector inside the quantum world. It's many parallel worlds inside the amplitude, but when I measure, every time I only measure just one of the states, so I'm not really getting the state vector. If I want to get the full picture of the vector, the x that I'm looking for, so I have to measure again and again and again so many times that I'm already losing the advantage. And it's a good point to say that it is beneficial if this algorithm is coming in a bigger context, as people did in another complicated example with algorithms with Classiq. They embedded this algorithm inside a bigger one, so they can extract interesting information from this vector that they are curious about, and this is solving the problem and not getting the actual full picture. So it's important to say these disclaimers too, and this is kind of interesting challenges we are facing in the side of algorithms world. And it's also opportunity to tell that what BMW have done, Tammuz is working with them, and they are embedding this kind of inverting algorithm inside a bigger optimization algorithm for cooling system. So any other question before we move to the workshop part?
I think they're mostly about specifics of the algorithm, so I think it's probably safe to move over to the examples. So the two questions, one was having to do with how does the fact that you can have both complex amplitudes and phase encodings, how does this relate to the bit string of ones and zeros that you're hoping to get out at the end? So that hopefully will be clarified a bit by some of the example, but if there's any preliminary things that you want to say about that, we do have that question.
Yeah, it's a good question, because indeed, in the case of the encoding of the vectors I'm looking at in this algorithm, so the digital encoding, the zeros and one, is just holding the number of lines in the vector. So when this bit string equals 0, so it means that I'm looking for the amplitude of the first row, and when it equals 7, so it's for the 7th row. And the amplitude for each of the state is the actual interesting information, which is the hidden variable inside, and we will see it now during the workshop. We will decompose the stages one by one. It can be nice. Okay.
We have one other question that as Ron is transferring over. So is decoherence time sufficient to perform all the necessary operations? So that's a good question that depends on the hardware. So Classiq has several useful things which again very much follow Wolfram's philosophy on this, which is that the answer to that question for all current hardware is not always, right? So what we are more interested in, both as our strategy in quantum as well as what Classiq is helping people do, is as those hardware change over time, you can provide what are called state vector simulators. You can provide tensor networks that are classical methods of seeing what would come out of quantum hardware. And as the quantum hardware is built, you can make that available as well. So, is the decoherence time sufficient to perform all the necessary operations? That depends on what hardware you're talking about. In the meantime, there are these classical options that are available for simulating what would happen on the quantum hardware too.
Yeah, and maybe it's a good opportunity to talk about some things that I will not talk about in this workshop. That the compiler is not just giving you the allowance to run on a specific hardware, but it's also optimizing. The idea is that we are finding the optimal, we are holding different solutions for each of the high-level constructs. We can also automatically allocate more auxiliaries and make reuse like a garbage collector. This is the kind of thing that the compiler is doing. So if I want to avoid decoherence noise and to make my algorithm less sensitive to it, so when I choose my model, I would like to choose what I would like to optimize. Maybe I would like to reduce the depth of the algorithms. If it will be too long, it will be too affected by decoherence, and I can limit. I know that I don't have in the hardware more than 100 qubits, and I can also specify the exact hardware that I'm running on, so that it will optimize for this specific hardware. And I welcome you also to explore if it's something that is important to you, the performance and the size of the algorithm, so you can check the latest article by Classiq, Classiq synthesis design, whatever, archive. Yeah, so we demonstrate some of the performance of the compiler and referring to the code for running of it and comparing to different competitors and how it performs for different kind of complicated algorithms.
Yeah, that's a really good point. So on different kinds of hardware modalities, in fact, you would want to optimize for different things. And so it's a very important point to mention that by specifying, well, what do you mean by optimize this circuit? What is the thing that we're trying to minimize, because that's what this particular hardware struggles with. That's a very important feature.
Yeah, and maybe just as an example to what happens when you run on different hardwares, when, let's say, just this simple example, when I want to run in on IBM quantum computer, which is based on superconductors, so I'm asking what is the most fair implementation for this kind of algorithms. So we see this adder is I did not want this example, sorry. Let's try Ion's computer. I just want to make sure. I'm looking for what is the most fair implementation to implement an adder. So two main ways to implement an adder. One is the ripple carry adder, which is like a lot of control NOT gates, very similar to the classical algorithms. And the other one, when I choose, let's say, a neutral atom computer or this IBM computer that I showed before, it was more fair to use a totally different kind of adder, which is based on Fourier transform. This one is not based on Fourier transform and not doing it in the phase. good point to continue to the workshop now?
Yes, I think so. There's one other interesting question that I think we'll get to at the end, but yes, there is a question about time frame of when and what kinds of problems quantum results are starting to surpass what you can already do just with a fancy classical computer. But I think we'll hold off on that till we get at the end, where we talk more about the practical side of things.
Okay, that's great. And maybe this kind of question came from people who are developing neural networks applications. So if any one of you has developed some classical notebook in PyTorch for running neural networks, so I welcome you to explore the integration of Classiq with PyTorch, so you can take any classical layer and replace it by quantum layer more easily thanks to the integration with PyTorch. So, for example, quantum generative adversarial network. We can see. Let's see how do I define the quantum layer. So we see I define the quantum circuit separately, and then when I want to embed it into Torch, so you see it's very similar to a classical network, but I'm adding a quantum layer over here. Okay, so for those of you who, as I said, it's really, really okay just to follow what I'm showing, and you can also run it by yourself. My recommendation is to try to do the homework later. You get the notebook, you can run it by your own. John, does everyone has the notebook?
Yes, so as a reminder to folks, if you click the download today's materials, if you haven't already, you'll be taken to a folder that has the Wolfram Classiq algorithm example notebook file. So that's the thing that you'll be seeing right now. And again, if you haven't had the opportunity to install the library ahead of time, that's fine. You can do so at any point. Feel free to continue to ask us questions on that community Slack channel. Feel free to explore at your own pacing. One other note that for some of the functionality that uses Python, so as Ron mentioned, Classiq has a Python library. We also have implemented some Wolfram Quantum Framework functions that have a method goes to Classiq option. That's been the case for quite some time. So really one of the emphasis of these notebook examples is showing how if you are finding code out there or just find it natural to work as part of the workflow in a Python style code, then you can do that from within a Mathematica notebook, and you can go back and forth between the outputs of that and Wolfram Language for the parts that you plan to use Wolfram Language for. So that's one of the focuses of this notebook, aside from showing the high level, why is it useful to have Classiq and Wolfram working together? Practically, you'll also see how it's possible to go back and forth between a collaborator who's doing some of their work in Python and a collaborator who's doing some of their work in Wolfram Language.
Yeah, absolutely. And that it's also a good time to say that I'm really amazed by what, and you will see in a moment, what we could do with this combination of two kinds of environments. You will see very soon. Okay, so maybe to start with just technical things. So the notebook is composed of actually two notebooks. The first one is just doing HHL matrix inversion without any solving of differential equations, and the second part is how we take a differential equation, comparing it to the solution of Wolfram and doing it in quantum algorithms, comparing the results, which is very leveraging actually this kind of integration. So with the technical things, there are of course installations that you should do. This installation is installing the Python package inside the Wolfram environment. I didn't uninstall and install to make sure that you are in the latest Classiq version, which is 0.66.1. 0.66.1. Besides that, you might want to check that you can run simple Pythonic code. So Shift Enter will run the code. And the external session is just connecting to Python and to make the moves from Wolfram language to Python. And installation of Wolfram Quantum Framework to make all this kind of quantum operations that we'll see soon in the Wolfram framework. Another technical thing that I will jump to is the authentication to Classiq. So since the compiler is not running locally on your side, but on our side, you're running Authenticate. Sometimes there might be some problems with that. So as long as you are already registered, so when you run Authenticate, you get this kind of window. So you just confirm and you are authenticated, and this is okay. And if you are not yet registered, so this is the time that you should register. So you might want to do it while I'm speaking, but it's also nice to listen. I will repeat the explanation of HHL, but I will explain how practically we do it with Classiq.
Also, Ron, is it possible to increase the size a little bit on that notebook? I think some of the parts might be a little bit small for people still. Yeah, that's much better. Thank you.
Great, thank you. So I might run quick on the notebook. I will not go like line by line, because if you're really curious about it, of course, you can do it by yourself at the meantime. I just want to jump and emphasize where it's your opportunity to make exercises and where is the features that will help you understand how to develop applications. Okay, so back to our problem. We said that we want to invert matrices. We want to apply the inverse of the matrix A on B, and this is how we get X, the state vector. So here in Python, and we can also in Wolfram define the matrix. So here is a 4x4 matrix. This is the elements. This is B, 1, 2, 3, 4, 5 rows vector. The reason we are normalizing it is because the summation of probabilities must be always 1, because it's going to be quantum. And the number of qubits, as you see, is just the log of the size of the vector. So if the vector over here will be 1,000, so I will need only 10 qubits for that, and it will be used later on. So here we see how we can see the matrices, and of course we could define them in Wolfram Mathematica. Here is just a few assertions to make sure that the matrix eigenvalues are okay and we normalized correctly. Now I would like to show you, okay, I have the matrices, I have the vector. Of course, that I can also use Wolfram. For Wolfram, it's very simple to make a matrix inversion, especially in this size. It will be a bigger problem when we put a very big matrices. But since our problem is small, we can already see what is X, what is the solution I'm looking for over here. And I could compare it to the quantum solution and see if it did work correctly later on. Now here is the authentication that I showed you before we are starting to run the quantum part. And let's see how we design the algorithm using Classiq QMod language. So let's recap on the theoretical background. We said we have a vector. We said we want to apply the quantum phase estimation with the exponential of the matrix A, and to use it for applying the inversion, then with the amplitude loading operator. And let's decompose it now. Let's do it one by one. Let's start with the first step. How do I load B anyway? So I said that B is rows running from 0 to 2 to the power of number of qubits. So this is just, now it will be just 4 numbers with just 2 qubits, and Bi is this 1, 2, 3, 4 that we saw before. So this is the B, 1, 2, 3, 4. After normalization, this is the value, 0.1, 0.3, etc. So I get a list of numbers that I want to load. I want to prepare a state with such amplitude and probabilities. Now it's the first time where we see writing together quantum code. And we want to define a quantum function for loading B. And now it's a good time to tell you that if you don't want to see the solutions, so search everywhere, create a copy of the notebook, search everywhere where you see solution start and solution end, and just you can delete this part and try to do it by yourself. Use the Classiq documentation. In some location, we put links to our documentation, so you can use it and try it by your own. But the idea in a quantum function, we use the quantum function decorator. It's common in Python. We use this symbol. We want to load a list of classical numbers into an quantum array of quantum bits. So this is 2 qubits. So we say it's array of quantum bits. We call this variable res. How do we do it? With a function that's called prepare amplitudes. So it gets the classical list. We can also give it the error. So the reason we can give some accuracy is if we want to pay some accuracy for the loading, so we can actually reduce the depth. This is also kind of trade-offs that the compiler is allowing. And I want to load it into the res result register. So this is load B. And this is how I define the function. But this is just a function. It's not building the full quantum circuit yet. We want to build the main function, which is contained currently, just for the example, only loading of B. Later on, we will put more for the HHL in here. But this is the first line of HHL, and the main is defining the full circuit. Here inside the variables of main is everything that I want to measure at the end of the algorithm. So here I want to measure everything. I want to measure many times. I want to measure the result variable. Because I want to see that the amplitude was loaded correctly. And how it looks like, the general flow for any building of quantum algorithm in Classiq, based on the main function, I want to create the model. So I get a quantum model object. And this is where we give you as an exercise to check how you can define where do you want to run this algorithm. Here you can define to run it on a real quantum hardware. So we are integrated with the cloud, with IBM Cloud, IonQ, whatever. So you can define it over here. You can check the documentation exactly how to define it. But this time we want to run on a state vector simulator. And the state vector simulator is giving me the full picture of the quantum world, the amplitude, the phase, the digital value. It gives me everything. So you might ask now, why do I need a quantum computer? And this is because, as we stated in the beginning, I need so much big amount of memory as the number of qubits is bigger and bigger. So this kind of simulator is limited by 18 qubits. A regular simulator without the full picture of NVIDIA GPU simulator, you can get a 30 qubit simulator easily. You just have to say what you want to choose over here. So it mimics a quantum computer. It's not a real quantum computer. It just mimics it. We are providing it through the cloud. We are running it on Classiq cloud, and you can do it in this way. So I'm setting the execution preferences to be a state vector simulator. This is the general flow. And now I want to compile. So I defined a high-level model, but I want to create out of it a quantum program, which is like the assembler, like the program at the gate level in optimized way after I define what I want to optimize. and to see the circuit. So you already saw it before in the presentation of the platform. So this is after synthesis. This is after the synthesize command, when I send it to the cloud to synthesize and create and get the circuit back, and I do the show. As you saw, I can also prepare amplitude. So here is the example of prepare amplitude. In one click, you can do it also here to choose optimization parameters. So we see how we do it both in the platform and also from Python. So here is more qubits, so it's a bit more complicated, and this is the circuit. And in our case, it was just 2 qubits that I want to measure both of them, and I can execute the circuit both from this button by choosing on which hardware I want to run, NVIDIA simulator or IBM, how many shots, how many times I want to run it. And again, I can do it also from Python. So here I send an execution job, I get the job, I can go to make myself some coffee if it takes a long time, and to take a look if it's ready inside the IDE. So this is execution results of the state vector simulator. So I see that 0, 0, this is the amplitude. It's relatively small with the phase in colors. And we can check if there is a good match to what we wanted. And we also see it in Wolfram, this comparison. So here is another option how to design, to build the circuit in the Wolfram language. I just want to jump to the part where we are comparing. So we see in a Wolfram output the execution result. Here, John, would you like to tell about it? You added explanation, what is swap doing?
Yes. So as you're encoding these things, there's different conventions for where you want to store the information and which wires, right? And so in the circuit that was initially loaded, you see that the amplitudes are the same numerically as the vector you were expecting, but they're just swapped on the 0 and the 1. So in other words, the first number and the second number that you're seeing, you're going to have to switch those two in order to recover your original vector. And that just depends on what conventions are being used for where you're storing the information on which wires. So again, a lot of these details are handled for you whenever you are looking at circuits that you're developing at high level. And so, as you're making these choices about how to work with circuits, this is something to keep in mind.
Yeah, it's cool, and you can see how the swap behaves. The swap is important part. We will see the swap test later on. It allows us to compare circuits, and it's shown nicely over here. So I hope you are good so far. So we started with some warm-up example for the first part of HHL. Any particular questions that you would like to discuss about now?
So one question that we are getting a lot of has to do with where does the quantum utility come in? So to be clear, on examples of this size, classical methods are definitely more efficient than using the quantum algorithm for just a small problem like this, right? So again, the point of today's workshop is to explain what does the algorithm do. So on the example problems that you're seeing, the classical methods are of course going to be perfectly adequate for inverting some small matrices and for doing finite difference on like a small problem. But if you take this exact same algorithm and you scale it up to many more qubits, these are some cases where you would start to say, okay, so as the problem gets very large, and for certain kinds of matrices, the classical methods might not work as well as quantum methods do.
Yeah, and I think that if we will be patient enough and jump to the future of 5 years later, so this kind of workshops will hopefully show something which is actually impressive, because we will have, if the roadmaps of the quantum hardware is correct, we will have quantum computers available, and we will be able to show, look, which kind of such big problems we solved. And currently, just proof of concept.
And this also might be an interesting thing to clarify for our audience here. So, the hardware providers is different from a company like Classiq, which is providing access and tools for getting the most out of that hardware, right? So, in other words, being the company which is making a particular quantum device is a different role in an emerging ecosystem than companies that, let's say, are interested in providing user experience, or let's say companies that are interested as one of the services that Classiq provides in saying, okay, given some hardware that exists and given someone's high-level idea, how do you best translate that into something that the hardware can really do?
Yeah. Great, thank you, John. And maybe after a warm-up, now it's a great opportunity when we continue to the next steps and to see how we are encoding more complicated algorithms, because the quantum phase estimation by itself is a complicated algorithm to design. Of course, since it's such an important built-in function, we are providing it as a building function in the library. And just to remind you, why do we need it? We say that we have the eigenvalue of e to the power of 2 pi lambda when I give the matrix A. So what the quantum phase estimation is doing is extracting this eigenvalue lambda into a quantum variable, quantum number. Actually, if we remember quantum types, we said we have qubits. So the eigenvalue is quantum number in the language, and we see it shortly in a moment. So in the HHL context, if I start with some a vector B, which is composed of this amplitude of beta with the eigenstates, so thanks to the quantum phase estimation, applying it on the eigenstates is extracting the eigenvalues into a register just before the amplitude loading that we said that we need. And then what we should do, it's the same as we saw in the presentation before. We want to take this lambda and to load this as an amplitude to another qubit. So every time where this qubit is equal 1, so we get that the amplitude is the inversion of this lambda. And this kind of operation is not trivial. It's composed of many low-level gate operation, and this is also the kind of things that we will see now how are done in the language. So here is another simple example that I would like that we will experience together. What is this amplitude loading? So loading of amplitude from a digital register to become an actual amplitude. So here is X. So you see that the type of X is a quantum number with 4 qubits. All of them are for our fraction. This is unsigned. It cannot be negative, but it's a number running from 0 to 1. And here is indicator qubit, just 1 qubit that I want to amplitude to load the amplitude of X over here. So the idea of this spatial amplitude loading operation, which is unique to Classiq, is that you can give expression. So there is an interpretation of the type of X. So X is a quantum number, and I want for each values of X to match the amplitude in here. So what X is experiencing, allocation from the memory. Hadamard transform is the operation that is parallelizing all the 16 words of the possibilities of values of X at the same time. This is the quantum word with a superposition, all of the values at the same time. And in each one of the words, the amplitude of indicator qubit is matching to x squared, and I can do anything that I like over here, and to load amplitude and to see how it behaves. I welcome you to check the documentation of this amplitude loading. We are also optimizing these parts with some tricks we are doing to do it in the most efficient way. And the circuit to make amplitude loading looks like, okay, we prepared X to be a superposition of all possible values, and for each one of them, we want to load the amplitude. So I take the values from each of the qubits with some trick and some gate level operation. So now that the amplitude of this indicator qubit is coordinated to be the x square of it. And when I want to execute to look at the execution of the result, so I can see over here that for each value of x, so indeed the amplitude behaves like x squared. So for this kind of values of x, so I see it's equals 0.125. So I see that the probability that the indicator will be, this is exactly the amplitude that we loaded, that the probability is relatively low. And as x becomes bigger, so the probability of the indicator to be 1 is becoming bigger and bigger, and we can also check and see that it's coordinated with the x square, comparing to the cases where it's equal 0. This is the amplitude loading operation. Now we don't want x squared. We said that we want to do 1 over lambda. This is the kind of amplitude loading that we want to do. So we want to define a function very similar to this one, but we want the amplitude to be 1 over the phase the phase register is the lambda, the eigenstate that so this is a quantum number, and I want to load the value of this quantum number to be amplitude of this indicator qubit over here. So I do it by doing the amplitude loading. So I'm writing the expressions that I like. This is the coefficients, some constants that I need to apply because of the mathematics. This is this C over here. So this is the amplitude loading part for the HHL. And I did not say that in the algorithm, when I finish to apply it, so I want to uncompute and release the qubits to the original state. So I have to apply the inverse of the quantum phase estimation, which we also have built inside, which you will see now. And now I can fully see the blocks of HHL. So given list of B that I want to load, A, the matrix that I want to put inside the quantum phase estimation, the register or the variable for X vector, the phase for the lambda as a quantum number, and the qubit to do the amplitude loading. I want to do the load B, which we already done together as a first step. And then I would like to apply the quantum phase estimation with a reference to use the quantum function, which is the exponent of the matrix. So I give a unitary means that this is the operation that I want to apply. So it's exponentiation of the matrix A, which we get from the outside, we see in a moment. And this is the phase register, which we also needed for the quantum phase estimation. So within quantum phase estimation, I want to apply amplitude loading. And it means that when I finish, I apply the inverse of this one. So this is the full algorithm. And this is how we write HHL in Classiq. I saw some other languages, it's hundreds of lines. I know it's a kind of a promotion, but it's really this way. It's really more convenient and easier this way, at least for me. So when I finish to define HHL, I want to use HHL. So here is the main function, again, where I have this vector and exponentiation of the matrix A, which I will give to the HHL algorithm as an input that we saw before. This is the function we defined together. Some of you asked about the resolution. So the resolution of lambda, the eigenstates, depend on the size of this register. And as we choose it bigger and bigger, so the circuit becomes also bigger, and it affects the accuracy of the results. So here is the quantum phase estimation size. And now I want to be convinced that it's actually working. So here is again creation of the model running on a simulator, and I want to see how the program that I created looks like. Here is the HHL, preparing the phase. This is the lambda, and here I load B, preparing the state B into res, applying quantum phase estimation. The quantum phase estimation, this is the internal details of it, but we don't need to be aware of it. Just if we are curious to explore, maybe in another workshop. This is how we get all the eigenvalues. Then there is the amplitude loading part, doing the amplitude loading into the indicator qubit, applying the inverse of the quantum phase estimation. And when we, and this is how the circuit looks like, and we can explore. And the execution result, so here it's not very practical to understand the solution. We need to parse it, and we'll see in a moment how we do it inside the code. But visually, we can see that whenever phase register is equal to 0.3575, which is represented by bit string, but this is a quantum number, and result qubit equal 1, the result register equal 1. This is the line in the vector, and indicator equals 0. This is the amplitude, and this is the phase, and we can see higher amplitudes for specific states, which we will use later on to parse the results. So we synthesized, we showed the circuit, see how it looked like. We can count the size of it, etc. And here is some explanation. John would like to elaborate about how it's done in Wolfram.
Yeah, so we actually did have a question about this step. So in the this one here, you see it's showing just a high-level schematic of the circuit operator. In the previous one, we had showed like the full circuit imported from Classiq. So there in the notebook there, we're using the Wolfram quantum framework to import the chasm representation of a circuit. So chasm is not a language for doing quantum computing. It's just a language for saying, what should my circuit look like? And so that chasm representation is one of the things that Classiq can provide through their library after you specified a circuit in QMod, and then it's been synthesized into a circuit with specific gate operations there. So after you've got that chasm form or several other common intermediate forms, we can just import that into Mathematica, as is shown here. So if something of that size, the import step takes a minute. But then once we've done that, we've got that into Wolfram's native representation of that quantum circuit so that you can work with it in Mathematica. Now, this circuit is a lot of gates, and so you probably don't want to run that on your laptop to try to do the simulation of that circuit, which this is another reason why it can be helpful to go back and forth between platforms. Let's say you're working on your laptop, but you've created some circuit that turns out to be something that needs too much compute power for your laptop to be able to simulate it classically. It's possible to simulate it, let's say, but you just can't do it on your laptop. So in that case, again, having these service connections with our partners can provide resources that, okay, sure, I can study this thing in my laptop, but then if I want to execute it and get what's the result from it, it helps to connect with other platforms as well sometimes.
Yeah, exactly. And this is exactly the synthesize and execute commands that you see, something that is sending a request that is highly loading our servers and give you results quicker without loading your computer. Yeah, so we saw raw results of the histogram at the end of the circuit, but of course it can be beneficial to make some post-process to post-selection and to extract the information of the vector I'm looking for from the solution. So here is some classical code to do it, and this is the quantum solution that we got out of the histogram finally. And this is the classical one. And we can compare them. So we can take the two vectors and use a Wolfram function, take two of them, and to find the norm between both of them. And we see that the norm is almost 1, so we understand that it's very, very good result. We also see another kinds of norms in Wolfram language, or directly calculating it this way, distance between them, and actual comparison. So we see the state vector in orange, the quantum one, and classical, the expected one, which see that they are very similar, and the errors are very small.
Yeah, and I do want to point out in this other one that notice, so the second of those two bar charts, that even with the classical numerical solution, if you don't manually set the options for Mathematica to have either exact or very high precision, that any classical numerical algorithm will have some residual error as well. So the fact that you're seeing some residual error from the quantum version of this algorithm shouldn't be surprising. If you're familiar with numerics, there's always going to be some numerical error. It's just a question of how bad is it.
Yeah. Great. So we saw how we invert a matrix. So once you are familiar with this now, so I guess you already want to go to the interesting application and what can we do it with it. We said that differential equation is something that is very useful to solve real life problem. This is what we came from. This is also the title of the webinar. Here you have some hints for what can you do when you need to manipulate the data to get an actual solution. And let's jump to the use case. Okay, so here is a very interesting differential equation that I discovered from the partnership with Wolfram. It was about a year ago when John and Mads discussed with us about this Lanchester model, which is a combat model. Actually, there was someone in Wolfram community write a very nice blog post about what is the Lanchester model. This is a very old model of generals in the army who want to simulate what will happen in the war with differential equations. So they said so now we can see it in the notebook already, but they say that if the force of one group or the other one side is X, and maybe the enemy, let's call it the size of or the power of other group is Y, and T is the time, and we want to check how it develops over time. So we see that the changes dx of the group over time divided, this is division by dt, depends on the actual current power at this current time of x up to some constant. It also depends on how strong is the other side. When the other side is stronger, I might become weaker. So it depends on y. That's also true for the relation between y and x, or x to y. And also it depends how much fraction there is between both of them. So we said, let's say rabbits against foxes, something which is more natural because nobody likes wars. And we want to see how we can solve these differential equations with HHL, and you can follow the flow over here. So if you remember the finite difference method, so we say that I can build this differential equation by assuming just small steps. So assuming that x at some time t, I can call it I, like a running index for the steps, is affecting the next step by saying that x, the difference between two steps divided by the time difference is this thing, so we can move the xi to the other side. So we get an iterative way, which is saying that the next steps of x is depends on the last step of x and the last step of y. And we also need to assume that we start from some points, so we know how to build it continuously. So we can play with the mathematics a little bit and create actually a matrix which is describing exactly this equation. So I need to create relations between xi and yi and everything together as a multiplication of a matrix by a vector. This is just technically how we can fill in the matrix with the values, but just to understand what is going on, maybe we can take a look again. If you remember this shape of this diagonal shape of the matrix, if we assume that the first half part of the vector is x and the second half part of the vector we are looking for is y. So applying multiplication on x and y and comparing it as described in the equations over here can be described by matrix multiplication. So the vector rows represent two things. It's like tensor. So there is we need a bit that's saying if these rows belong to x or y, and we need a number that is saying what is the row which is matching what is the time step. So first row is the first time step, and then we continue this way. So the amount of time steps multiplied by two groups define the size of the vector. Questions about this part?
So quick comment to the audience. So we probably will go maybe 10 to 15 minutes over the scheduled time. So there is a recording if you are needing to dash right at the scheduled end time. But it's good that we've had so many questions. We love the engagement. Feel free to put more questions in. So we do have some questions about the Chasm file import and other parts about using Classiq from within Wolfram that I think we can comment on. Do we want to quickly show the result of running this algorithm so that we can see the comparison between the three methods, the classical and quantum finite difference, and then we can get into some of the more general Q&A questions, I think.
Yeah, great. I will go over, not like step by step, I will very shortly go over the algorithms because you already saw the HHL and the core here is HHL. Everything I described here is just how do I build the matrix. But once I have the matrix, it's the same HHL. So we choose some example of these coefficients of how this war behaves, how what is the natural death of rabbits and foxes and everything, and you can explore it. And it's actually defining the matrix. So once I have the matrix here chosen with 8 time steps sampled every 6 years, so we can see what we are actually curious about is how does giving this differential equation, which is very cool that I can define in Wolfram language, with these differential equations, I want to see what will happen to the rabbits and foxes in 50 years or something like that, assuming I know how they behave currently with each other. So here is a differential equation, and this is one of the coolest things in the integration with Wolfram, that we can give this differential equation and actually get an immediate solution out of it, which is very, very cool, and we can use it to compare it to the quantum solution. And here is how we can, another way to solve it in Wolfram Mathematica with the finite difference method, we also can store these two kind of methods for the comparison to the quantum part, and then building the HHL in the same way with these matrices and vectors, just putting inside another matrix which represent a real problem now and not just a matrix. Here defining the amplitude loading again, everything the same way of extracting of the results, and now we can check and see that the results actually has a good match. I know it's skipping a lot of lines, but this is like the boring details which you, if you followed well, you already understand correctly. I want to jump to the quantum solution from the HHL, the vector, with the classical solution. So here you see the HHL is the quantum solution. One thing that is different in how do I define the quantum algorithm for it, which is interesting to see, is that if before we have just quantum array of qubits, now there is a meaning. We say that the vector is time step, which is a quantum number telling me what is the row, and a qubit telling me if this is rabbits or foxes, and everything is going inside the quantum struct, which is like object-oriented language. So I can use this state vector as an actual quantum struct, but here it's the same HHL. So I can use this interpretation of types of quantum variables to easily post-process and say, okay, this is the time, this is rabbit and foxes. So I can easily extract the information for the foxes and the information for the rabbits separately, and seeing that the result has a very good match with the classical solution by Wolfram, or if we measure how far are them from each other, so we see high percentage of a match. Maybe a good point for questions and for people who has to leave soon. If someone wants to stay to talk about anything else, to ask more questions. But I think once you get it and you have the example and you use the notebook, so you can try to think about your own kind of applications. And as I said, you can also explore in the user guide and say, okay, let's see another kind of differential equations. So here's the Poisson equation and things like that. And you can explore what are you curious about? How can you leverage quantum computers for your own needs and to try to plan for deduction purpose currently and maybe for publication and research. So we will be very prepared to the quantum computers that are already here, but growing actually pretty fast.
So this plot here and the fidelity at the end, I think, are really the punchline of why quantum algorithms are interesting, is because using the classical finite difference method, using again what was it, 8 time steps, excuse me, six time steps of 8 units each. The agreement between those is quite good. And then this example problem is one such that we have classical methods available to us, like what ND-solve, our function, uses, that we can see what's the ground truth solution, so to speak, in this example problem. We had a lot of Q&A questions that were coming in that had to do with, can we speak a little bit to what's the state of not problems like this, where the classical methods are, of course, perfectly fine, but that regime where quantum is starting to be interesting, not as only a future thing, but as the current hardware is starting to appear pretty interesting in terms of providing alternatives to what you can do with classical simulation.
Yeah, so a great and interesting question. So there is some doubt around the world about what can we currently already do quantum algorithms. There is the NISQ era, which means like a noisy intermediate scale of quantum computers. There is a claim that you can run some kind of specific kind of problems on today's hardware with the noise, by mitigating the error and get immediate results. There was also a proof by Google like a year ago of, look, we actually got some advantage from a current quantum computer, and then became another article showed we can do with a classical computer the same and just a bit better. But most of the time, these kind of algorithms are at the regime of optimization. There is a famous algorithm called QAOA. So you can explore in the user guide different kind of optimization algorithms. So here is electric grid optimization. So another kind of example where you can define the optimization level, the optimization problem at the high level. Here is on a graph. Here is the linear programming. So you can define with Pyomo package or by your own with the high-level quantum types what is the optimization problems that you want, what is the constraint, what is the objective that you want to optimize, and to see how the optimization problem converge. I refer you to this example because if you are curious about immediate kind of advantage, this might be relevant, even though there are some doubts around the world if this kind of algorithms bring advantage, or you actually need to wait for the really big and quiet quantum computers.
So we had some other Q&A where people were interested to know, so how does the translation of the high-level idea into a specific gate set, why is that important, and can you speak to some of the challenges of that? And that, I think, really is sort of where Classic's technology shines, because it's possible to define this HHL algorithm using a set of gates that might look fine, but in fact can't run on any current hardware. And in fact, there's lots of examples of defining circuits that will implement HHL that they look more concise, and they are a lot easier to simulate on like a classical computer, but it's some gate set that isn't actually supported on quantum devices. So yeah, Ron, if you could comment on that for a moment.
Yeah, sure. Thank you. First, regarding gate set, we are aiming to any gate-based quantum computer. So we don't need to be integrated with a specific backend. As long as you mentioned what is your basis gate and what is the connectivity map, which can be done from Python 2. So we are able to optimize for this hardware. So it might look like a bit of magic behind the scenes, but I would like to show you what I mean by optimization. What we are doing is we're taking this high-level language and trying to check at the big level and optimizing what is the smallest circuit for this specific connectivity map and basis gate. We are solving a CSP constraint satisfaction problem optimization algorithm. The basic idea, this is the core of the technology, actually. This is what we are doing, shrinking circuits. The idea, different from transpilation, from whom you know, it is changing a little bit the gates to match to a specific hardware, and maybe optimizing the depths a little bit, which is something that Classiq is not developed by ourselves, but we are using it, but we did not develop it. The idea of the compiler is to run on bigger possible implementation space for a given high-level language. We are exploring for this specific hardware what is the best one. So one of them will use maybe more qubits, but maybe it's worth it to reduce depths and maybe to make a reuse in another places. So there is also, so we are running on different implementations. We also manage the memory. So we are optimizing by, if we see that some function finished with its qubits and it's free to be reused in another function. So we are managing it, and automatically uncomputing and releasing the qubits automatically by the engine. So we can see nice trade-offs. I welcome you to check in the article that I showed before how the technology is explained deeply with examples and comparisons. I hope it's answering the question somehow.
I think so. We had a question about the HHL algorithm and how would results possibly differ if we were using a backend that had different connectivity or topology or something like that. It's a very interesting question, very big question.
Yeah, indeed. So if you remember, I showed you before an example where we chose a very simple case where I just want to make addition of x plus y. So we saw that if we choose some one backend, so we are storing the connectivity map and basis gate of this backend automatically. We are taking it from IBM Cloud, and when we are running with the different implement, we are taking the different possibilities of how to make an adder, trying to do it with this connectivity map, with more auxiliaries or less auxiliaries. We can use extra spare qubits just to maybe to reduce the depths. So we are getting one implementation when we wanted to optimize for depths, but then we saw that when we choose another kind of backend for ions, so we see that when we are running on different possibilities of how to make hardware, so we get a totally another implementation, which is also optimizing for depths, but is using another kind of no, this is the same as IBM. It chooses the same thing, but we saw before already. So that if we choose the basis gate of neutral atoms, so we get another kind of adder.
And some people might have had a poll popping up over part of what you were showing in the first part. So if they didn't get to see the comparison there, my apologies. But yes, so what you get back from different hardware, they will have different sources of error. The whole place in the ecosystem for figuring out how do you translate the high-level algorithm to these various backends is a very interesting and needed role. So that hopefully answers that question. Let's see what other questions we have. We're seeing a lot of thank yous for the presentation. So Ron, great work. It looks like people are enjoying it.
Thank you for attending.
Yes. So we also had a question about Notebook Assistant and how this relates. So Notebook Assistant, for those of you who have not seen that before, uses a large language model as well as a bunch of internal tooling that we've developed to be really good at helping you with Wolfram language code that comes from built-in functions. It's not yet an expert at our Wolfram quantum framework, other Mathematica packages that people might have developed out there, or for example, using our integration with Classiq library. However, we are actively working on tools so that the Notebook Assistant will be better at helping you not just with general Wolfram language and built-in functions, but with anything out there in the Wolfram ecosystem. So it never hurts to try asking the assistant for help with one of those things, but it is not yet an expert in some of these things. It does a better job, using the things that we've set it up to be an expert at. However, Ron, I don't know if you want to comment on, if you use even just like ChatGPT or something, it knows a fair amount of Mathematica, for example, because it's just out there on the internet. Maybe if you've experimented, how good are just the sort of out of the box, not doing anything special language models with helping people with your stuff?
So actually, I'm using ChatGPT and Copilot a lot for QMod. So Copilot by GitHub, we can integrate it into an environment for developing code. and it's recognized, it's understand the QMod easily from context because it's shorter and it allows me to develop algorithms, new algorithms, by understanding from context. So, for example, I wanted to make quantum dots Hamiltonian chemistry example, but I add only another kind of material in chemistry example. So I took the example and it understood from context, build the Hamiltonian for quantum dots because it already know what is quantum dots. So easily to build with Copilot quickly and easily. And of course, also ChatGPT, I give it to learn from reference, and it also knows what QMod is. Not so much like Wolfram Mathematica, but there are not so many examples, but I also load it with example to understand from context, and it's very, very useful for developing QMod.
Yeah, that's a good point, is that any of these code assistant tools, even if they're not yet set up to sort of be an expert in something, if they just see a few working examples, they are pretty good at generalizing that to what you want to do.
Mm-hmm.
So I think those are the main questions that we've had. Again, I want to draw everyone's attention to the invitation to the community Slack channel. We do want to make sure that we continue the conversation. Of course, if you have any posts that you want to make of cool things on Wolfram community, by all means, please do so. Also, stay tuned. So this is based off of one of Classic's great documentation examples. We should have some interesting community activities for people to, combine these technologies together as I don't want to say a hackathon exactly, but sort of an informal thing. So stay tuned for events like that coming up.
Yeah, totally. And I welcome you to if you wonder how can I easily access all this kind of material, so just please feel free to register. You just type platform.classiq.io and you are inside, so you can quickly find where the user guide is to see the kind of example, to connect to the community, to the Slack over here at the left, and easily try to do things by your own. We are very excited and interested to do more interesting things together with you. Please feel free to contact through the community or personally. I'm very happy to make more interesting projects together with you.
Thanks very much to Ron for being our presenter today.